by looking at problem 29. This is in chapter 1 of your text. Okay, so there's a system of elements, and then each one of these elements is labeled. And then next, the author is going to give us voltage and current information. So just a reminder what we said last time. When you define a current, because of the bipolar nature of charge, we're going to need both a direction and then a magnitude. And then with polarity for voltage, that's what's going to be needed in addition to the magnitude. So with that, here's what the author of the problem has assigned. And then finally, the voltage are specified as shown. Okay, so I'm going to try to, right from the start, emphasize some important things to consider when you're analyzing circuits. First and foremost, try to be as neat as possible and as systematic as possible. That will just help you eliminate some careless mistakes. And then the other thing we started to discuss last time, I want to continue to emphasize this. As our circuits get more and more complex, it's going to be pretty challenging to, in all cases, know ahead of time the voltage polarities and the current directions. So what we're doing here is simply assigning a direction to current, assigning a polarity to voltages, and I'm not really giving it much more thought than just putting something down. What's going to happen is if we are systematic and careful, the signs, particularly in the context of the passive sign convention, they're going to take care of themselves. And that's one of the main things this example will hopefully demonstrate to you. Okay, so while we have an opportunity, let's go back to some of that circuit terminology. So how many nodes do you see in this circuit? Okay, so it's sounds like the consensus so far is 6. So let's just quickly look at the points where 2 or more elements join. That's how a node is defined. So we've got one there, one there, and then don't overlook, based on our definition, that this is a node and this is a node. So yeah, those of you that were indicating 6, that is the case. Okay, recall that a loop is defined as any closed path in the circuit. So using this same one as an example, how many loops do you see? Okay, there are 6 loops as well. So in other words, we've got a loop here, here, here. You could do the right hand 2/3, you can do the left hand 2/3, and then you can go around the entire system. So again, 6 is correct. And then finally, how many meshes? So a mesh, we said, is a loop not containing other loops, so the meshes in this case, 1, 2, 3. And I just always encourage you, take opportunities to get comfortable identifying meshes and nodes in particular, because we are going to deal with methods that require that you're real comfortable with that concept. Okay, so now to the problem at hand. Here again, to be systematic, what I would encourage you to do is consider, because you have something like this on your homework, so consider setting up a table. Conservation of power means the total power absorbed in the system has to equal the total power that is delivered in the system. And so in the process, the author of the problem is trying to illustrate an important aspect of what we call the passive sign convention. Let's just run through this for the 8 elements here. And then once we do a couple of these, I think it'll be pretty clear the approach and how we're interpreting things. So let's just start with this element labeled A. So all we're asking is, what type of element is that? Is it a source, or is it a load, or other terminology, is it active or is it passive, based entirely on how this is labeled. So what do you say in terms of this first element? Okay, so if you go back to what we described last time, anytime you see current entering the positive terminal of an element, that's the passive convention. So based on our circuit, that's passive. We then established with this convention that if you have a passive element, the power is simply V times I. And I should point out, if you've got your textbook, they have a table of voltages and currents. So that's where these values are coming from. And here's another opportunity to just point out some things to watch for to minimize your frustration. Please look at units carefully. So in this particular case, all the voltages are given in volts, all the currents are given in milliamps. So our power are going to be in terms of milliwatts in these cases. So based on the calculation, we get a positive 10 milliwatts. So what is the element based on that calculation or computation? What was our statement in terms of the passive sign convention? Positive number means what? Anytime you see a positive value, you know that element is absorbing power. So it absorbs power. All right, so having that first one as a guide, let's run through the remaining ones here. So based on what you see, what type of element is B? It is active. Current is exiting the positive terminal. Remember, with this convention, if we have an active element, our calculation is minus V times I. And I can't stress this aspect enough, particularly for what comes later. You've got to pay attention to signs or it'll drive you crazy. Okay, so we had a minus 3 milliwatts. What's the interpretation based on the computation? Anytime you see a negative quantity, that in the context of the passive sign convention means it's delivering power. So it is active. All right, what about element C? What does everybody think as you look at the voltage, polarity, current, direction? Yep, that is active. Okay, so when we apply that passive sign convention, active element minus V times I, we have minus 7 volts times negative 2 milliamps. So our result is 14 milliwatts. What's that telling us? It is absorbing that, so it is in fact actually a passive element. Now, you may not thoroughly appreciate this yet, but what that's telling us is, as long as we keep track of the signs, this convention, in the end, will tell us which elements are supplying power and which elements are delivering. So there's really, that's the beauty of the passive sign convention. And as I said, you need to get familiar with it because we will utilize it from this point on. Okay, what about element D? Yep, active is shown. So similar conclusion to what we found for element C. Okay, what about E? Yep. Passive as shown, the current's entering the positive terminal. So you'll notice when we plug the numbers in, passive, so we take plus V times I, but then the actual voltage is negative 20, so we get a negative 100 milliwatts. What's the interpretation? It is active. It's delivering that amount. Okay, what about F? Yep, passive. Positive value absorbs power, passive element. Okay, so thankfully or mercifully, we're getting towards the end. You're probably tired of this process by now, but what about G? Yep, that is, as shown, it's leaving the positive terminal, so active. So again, being attentive to the signs, the computation minus 6 milliwatts, so that's delivering that amount. So it's active. And then finally, what about H? Yep, it is passive as shown. Positive 36 milliwatts, so the final element is absorbing power or is passive. So in other words, we started with that column to essentially establish how we would set up the calculations, but in the end, it's this column that establishes which elements are active or acting as sources and which are acting as loads or are passive. Final check then, is power conserved? Yep, as you look at this, we've got, let's see, delivering, yep, 109 milliwatts delivered, and when we add up what's being absorbed, and thankfully, because we're not trying to disprove this fundamental, so the amount of power absorbed does equal the power delivered. So there's our final check. So that's going to be a familiar question from this point on. I mean, we can always see if from a system perspective if things are accurate if we get a power balance in the system. So any questions on that? Again, I will be pleading with you, try to develop real systematic approaches, and I think you'll find circuit analysis is a relatively painless process. It will work nicely if you just pay attention to the details. So as I'm erasing this circuit, this is really the last time we'll treat circuit elements as just blocks. So our goal now is to begin to develop a set of circuit elements that we're going to deal with. We'll always approach these the same way. What I mean by that is when I introduce a new circuit element, I'll always do that in terms of its IV characteristics. That will allow us to build mathematical models if we can do that. So what I'd like to start with then is a discussion of the various sources we're going to deal with in this class. So we'll start with what are called ideal or independent sources. And here's another place where you may be extremely confident in your understanding of these elements. But if you're a little bit careless, you may in the process violate the IV characteristics that we're going to discuss. So that's something I'll be mentioning throughout the semester. So let's start by looking at an ideal voltage source. So first, the schematic representation. Will look something like that. So an ideal source is depicted using a circle for the schematic symbol. Notice I'm using the active convention here. So for the given voltage polarity, treating that as a source, the current's leaving the positive terminal. So would anybody care to come up with some words describing what is the role of that source? What do you know about that source? Okay, we will be in the course of this semester looking at AC circuits, alternating type of signals, and we'll also be looking at DC or direct current type of signals. Actually, the first part of the course, we will look strictly at DC type of signals. So, we'll address that in more detail later. But the thing I want you to consider is this source is going to deliver a prescribed voltage across its terminals regardless of the current flowing through it. So that's the key thing. And the reason these are called independent sources is because another way of stating this is it delivers that voltage independent of the current that's flowing. All right, I tend to be a very visual type of learner, so another thing I like to do here is to kind of visualize what this means if you draw an IV characteristic. I think that's worthwhile too. So if I asked you to plot the characteristic of an ideal voltage source, what would that look like? Just a a vertical line in this case. In other words, that source delivers the voltage Vs regardless of the current that's flowing. All right, now I also know that anytime you see the term ideal, you might be a little bit skeptical because you recognize nothing will truly deliver that type of behavior. But can you think of a practical example that maybe comes close? You might, some common examples, maybe like a car battery. I mean, that can deliver 12 volts, and it can deliver a lot of current over that, for that 12-volt range. Another thing, the power supply coming from your local utility. So this wall outlet, certainly there's not a lot you can do as a residential customer to alter the voltage that's coming out of the wall. So that's another example. They approach that ideal behavior. All right, let's move then to an ideal current source. Once again, because it is an ideal source, we'll use a circle. Because it's a current now, we'll indicate the direction and then a magnitude. As before, I'll assign the polarity of the voltage because we're treating this as an active element or a source. So what's this source's role in the circuit? Exactly. It will deliver this current independent of the voltage across its terminal. I think it stands to reason if this is the plot of an ideal voltage source, what's the plot of an ideal current source going to look like? That's just a horizontal line in this case. Can you think of an example of something that performs like that? This may be less well known. Over a limited voltage range, a PV or photovoltaic cell will act very much like that. It drops off rapidly after the voltage gets too high. But that's another just example that approaches that type of behavior. Now, one final question before I address some other types of sources. What determines, in this case, the current that's flowing from that voltage source, and in this case, the voltage that's across the current source? So what do you suppose determines those quantities? Yeah, the resistance or whatever you've attached to that circuit. So until we know what's attached to the utility, the wall outlet, you can't say what current will be supplied. So that's an important perspective too. Next, I want to mention what are called controlled or dependent sources. And maybe by a show of hands, how many of you have had any prior experience with those? Okay, so basically one or two out of the, that's what I would expect. This is essentially a little more advanced than what you do in maybe a physics 2 circuits perspective. So here's the reason we're needing to define something like a controlled or a dependent source. When we start trying to model electronic devices, this is going to be very useful. Now, in this course, you'll get a lot of experience with one particular electronic device, and that's what's called an op-amp. In Chapter 5, that will be our focus. So in Chapter 5, we're really going to need to rely on this type of modeling. So when we hit Chapter 5, you're comfortable with analyzing circuits of this type. We will make sure and use a number of examples that include dependent sources. So here's the basic idea behind this. Again, here's the basic idea behind a controlled or dependent source. The voltage or the current of the source depends on another voltage or current elsewhere in the circuit. You'll recognize dependent sources. Now, instead of using a circle as we did for an independent source, we'll use a diamond to designate a dependent source. So again, this voltage or this current is going to depend on another voltage or current somewhere else in the circuit. From that description, how many types of controlled sources are there? If you think about that, the way we've defined it, shouldn't there be a family of 4 dependent sources? I'm going to label the 4 types as follows. So you might have a voltage, dependent voltage source that then is a function of another voltage somewhere in the system. So this is what's called a voltage-controlled voltage source. And in the interest of time, we'll just use the acronyms from this point on. So VCVS is a voltage-controlled voltage source. So another type would be this voltage now is a function or depends on a current elsewhere in the circuit. So that would be called a current-controlled voltage source. Then we take the same perspective for 2 types of current sources. So the current in this case depends or is a function of a voltage. So that would be called a voltage-controlled current source. And then the final type, this current depends on a current elsewhere or a current-controlled current source. At first glance, that may seem a little bit confusing, but we will, starting early next week, look at some examples that include this type of device, and I think you'll be very comfortable with how it's treated. Yes, sir? That's just what the author chooses to do. In other words, they're just saying that here's some function, and so that's how they choose to define that. So I just want to remain consistent with what the text is doing. Yeah, if you look at another textbook, they're likely to define that much differently. But the key is it just is a function of some other voltage or current. Any other questions on that? All right, so let's move next to a device I'm sure you all have experience with. That would be a resistor. Okay, in the context of our earlier discussion, what I mean by that is our power discussion. What type of element is a resistor? It's always passive. In other words, it absorbs energy from the circuit. You know that's the case because if you touch a resistor that's operational, they're typically warm because they are dissipating energy in the form of heat. I would imagine the schematic symbol that you've seen, much like what I've just sketched on the board. So this represents a resistor. Now, because it's a passive element, just want to stress that we want to adhere to the passive convention, so the current flowing into the positive terminal. What law describes the IV characteristic here? Yep, Ohm's law. And just a quick reminder, units here of resistance. A volt per amp, or what's a more common description of a volt per amp? An ohm. And we use omega to designate an ohm. So there's a linear relationship between voltage and current for resistor. So the IV curve would look like this, where the slope is the reciprocal of resistance. Let's quickly revisit power from the perspective of a resistor. So just want to emphasize, as always, power for a passive element is plus V times I. And also emphasize, since we have Ohm's law relating voltage and current, we're certainly justified to represent voltage as I times R. Or you would be justified to represent the current as V over R. So it's convenient when you're thinking power and resistors to essentially have these three forms in mind. And I will encourage or tend to use the one that I have the most information about, so it'll be the least amount of work to get the result. This is also a reminder, since you're squaring the current and squaring the voltage in those latter two forms, that that number will always be positive. So that's an indication that a resistor will always absorb power. So you can see that passive sign convention at work again. Actually, I brought couple of samples in here just to emphasize a point here. These are two equal resistors, and what I mean by that, they have the same nominal value. These are both 200 ohm resistors, but you can see big difference between the two. This is a resistor that's rated for 1 watt. This is a resistor that's rated for 200 watts. So just want to emphasize ratings is extremely important if, as an engineer, you're trying to specify a design and you send your design down to have somebody build it. If you intended to have this in the circuit and you didn't give any specifications and they put this in, you can imagine this will probably melt under the heat that this one was supposed to be able to absorb. So again, pay attention to ratings. That's another important specification other than just the nominal resistance. Now, I introduced resistors by observing that I think everybody in here has worked with resistors. How many of you have worked with the concept of conductance? Again, couple. That's typical. So it's going to be convenient at times to work with the concept of conductance. So conductance we'll designate that with a capital G. Conductance is simply the reciprocal of resistance. As it turns out, we'll use the same schematic symbol, which is potentially confusing unless you pay close attention to units. So again, passive element, passive sign convention, and so there's the schematic symbol of a conductance. So units on conductance then will be the reciprocal of units on resistance. So instead of a volt per amp, we now have an amp per volt. And under the International System of Units, this is what's called a Siemens. And I mentioned last time that my area of specialization is more in the power end, so I do want to mention to you that there is still another unit used for conductance, primarily in the power realm. This just points out how creative we power engineers are. We spell ohm backwards, so it's called a mho, and we invert the omega. So you should just be aware that both of those will be something you might encounter. I recognize going through the review of the circuit elements isn't the most riveting lecture material, but it's a necessity in that we need to all have the same understanding of how these devices operate electrically, so as we put them into circuits, we can build mathematical models to then analyze the performance. What I'd like to do in the time remaining is look at one more example. This is now in Chapter 2. On page 50 of the custom text, And this is fairly representative of a couple of the homework problems that have been assigned. What I mean by that is you'll hear the following question posed. It says, looking at this figure, if the interconnection is valid, essentially prove that power is conserved. If the interconnection is not valid, explain why. So I guess what I'm asking you to consider then is, how are you going to establish when something's written in a text, or I write something up on the board, if that in fact is a valid interconnection? Because unfortunately, I can write anything up here, regardless how ridiculous it might be. So that's what this is really having you look at. So you have any idea how you could establish if something is valid or not? Okay, so the observation up front here was that essentially everything's conserved, so that's exactly right. Remember, last time we said KCL is a statement of the conservation of charge. KVL is a statement of the conservation of energy. If a circuit that's sketched violates either one of those two essentially fundamental cornerstones of physics, then the connection can't be valid. So that's really all we're asking you to look at. If you look at this from a KVL and KCL perspective, do you see any problems? So a quick reminder, conservation of charge, KCL. The net current entering any node must equal 0, and then KVL, we focus on closed paths or loops. The net voltage around any closed path must equal 0. So as you look at this circuit, is there anything about this circuit that violates either one of those two principles? Yep. So absolutely see a few people shaking their head. So that's a good sign that you're, what I'm interpreting, if you look at that left-hand mesh, let's write KVL around that. The way I interpret KVL may be a little differently than what your physics instructor described, but the bottom line is there's many interpretations. As long as we all generate the same equation, I don't care what perspective you take. What I do is somewhat mechanical. So if I go around this mesh in a clockwise fashion, I'm just going to write these in terms of the sign and counter first. So I have plus 10. Continuing on that same basis, plus 20. Notice I'm back where I started. So KVL says the algebraic sum of voltages around any closed path must equal 0. Well, obviously, that's not the case, so this interconnection is invalid. Some of the rest of you might have looked at this system and recognized that these two elements are in parallel, and you hopefully recall that parallel elements must have the same voltage across them. So many ways to interpret that is not a valid connection. So with that, we're out of time, so have a good weekend. We'll see you on Monday.